Welcome to another deep dive. We always try to bring you content specifically catered to your interests. And well, today we're diving into something I know a lot of you have been wanting more of, exoplanet formation.
hmm
So specifically, we'll be exploring a recent scientific paper titled, Where in the Milky Way Do Exoplanets Preferentially Form? And this paper tackles a really interesting question. Does the location and timing of a star's birth within our galaxy influence its chances of forming planets?
Right.
And if so,
Yeah.
how?
How? Exactly.
It's a big question.
Yeah.
And this research goes beyond simply identifying the presence of planets.
Mm.
It's really looking into the galactic context of their formation, which adds a whole new dimension to our understanding
Yeah.
of planetary system.
It certainly does. And for this analysis, the researchers utilized two extensive star catalogs, Sweet Cat
Hmm?
and HARPS GTO. And, as our listeners probably know, these catalogs provide a wealth of information about stars, including whether they host planets and a range of, crucial characteristics. Yeah, and these catalogs are absolutely essential tools for astronomers because they allow us to study stars
Mm.
with diverse characteristics,
Right.
which ultimately enables us to glean these insights into the intricate processes governing planet formation.
hmm Now, the paper's first key finding centers on the critical role of metallicity in planet formation. So could you elaborate on what metallicity means in this context
Sure.
and why it's so important?
Yeah, so in astrophysics, metallicity refers to the abundance of elements heavier than hydrogen and helium within a star. So these heavier elements, they're the building blocks of planets. Think of it as a cosmic recipe. You
Right.
need certain ingredients to create a planet, and these heavier elements are just essential
So
components.
a star with a higher metallicity has more of those crucial ingredients to form planets.
Exactly.
Okay.
And the study's findings support this notion. They discovered that stars hosting planets generally exhibit higher metallicity compared to stars without planets, suggesting that regions of space richer in heavier elements are more conducive to planetary system formation.
Now, the study also found something really intriguing. Stars hosting massive planets like gas giants have even higher metallicity than those hosting lower mass planets. So what does this suggest about the relationship between a star's composition and the types of planets it can form?
This finding suggests a compelling link between a star's metallicity and the size of the planets it can host. It seems there's a threshold of heavy elements required to form these massive gas giants.
Mm.
Perhaps a certain abundance of these elements is necessary to trigger the formation process or provide sufficient material to create such large planets. It's like
Yeah.
a cosmic construction project. You need a certain amount of raw materials to
Right.
build something massive.
Yeah, that's a fascinating analogy. Now, aside from metallicity, the paper highlights another key factor influencing planet formation, the age of the star. So what did they find in this regard?
So the researchers observed that on average, planet-hosting stars tend to be younger than stars without planets. Now, this might seem counterintuitive initially, but it becomes clearer when we consider the concept of galactic chemical evolution.
Galactic chemical evolution.
Yes,
That sounds intriguing. Could you explain this concept for our listeners?
certainly. Essentially, the Milky Way galaxy itself has evolved over billions of years. In its early stages, the galaxy possessed a lower overall metallicity. But as stars lived and died, they produced heavier elements through supernova explosions, gradually enriching the interstellar medium, the space between stars.
Ah, so newer stars are forming in an environment that's already richer in those planet-building materials.
Precisely.
Okay.
This explains the observation that younger stars are more likely to host planets. They simply have more of the necessary ingredients available to them. It's like comparing a bakery in its early days with a limited selection of ingredients to a well-established bakery with a pantry full of diverse components. The latter has more options for creating a variety of baked goods.
Right. Okay, that makes perfect sense. So the early Milky Way, with its lower metallicity, might have been less hospitable to planet formation compared to the galaxy today.
That's a plausible conclusion. The early Milky Way was a less enriched environment, particularly for the formation of massive planets. As the galaxy evolved, the gradual increase in heavy elements created conditions more favorable for planetary systems to emerge.
So this really paints a picture of the Milky Way as a constantly changing entity, with those changes directly impacting the potential for planets to form within it.
It certainly does. The Milky Way is far from static. It's a dynamic and evolving system, and understanding its evolution is crucial to deciphering the history and prevalence of planet formation within it.
Now, shifting our focus slightly, the paper also dives into the concept of galactic birth radius, referring to the distance from the Milky Way center where a star is born. So what insights did they glean from exploring this variable?
They found a significant correlation between a star's birthplace and its likelihood of hosting planets. Stars with planets tend to have formed closer to the galactic center than those without planets.
That's interesting. What might account for this correlation?
Well,
Why would location play such a significant role in planet formation?
the inner galaxy is a much denser and more dynamic environment. Stellar activity is more intense, leading to a greater concentration of heavier elements generated through supernovae. These denser, heavier element-rich conditions appear to provide a more fertile ground for planet formation.
So it's like prime real estate for planet formation.
That's a great way to put it.
Okay.
The inner galaxy seems to offer the ideal conditions, the building blocks and the energy to kickstart the planet formation process.
Now, all this discussion about metallicity, age, and location leads us to a pivotal concept: formation efficiency. Essentially, how likely is it for planets to form around a star? What did this study reveal about how these factors impact formation efficiency?
They meticulously examined how formation efficiency fluctuates based on metallicity, age, and birth radius. And their analysis revealed some consistent, fascinating trends. As we've discussed, higher metallicity correlates with higher planet formation efficiency, meaning that a greater abundance of heavy elements generally leads to a greater likelihood of planets forming.
That makes sense. The more building blocks you have, the more likely you are to successfully assemble a planet. What about the role of age in formation efficiency?
Interestingly, for high-mass planets like gas giants, the study found a strong correlation between younger stars and a higher formation efficiency. This suggests that the processes involved in forming these massive planets are more efficient in the early stages of a star's life. For low-mass planets, the age dependency was less pronounced, though they did observe a slight increase in efficiency at intermediate ages.
What about location? Does a star's birth radius influence formation efficiency?
Indeed, stars born closer to the galactic center where the conditions for planet formation are more favorable generally demonstrate a higher planet formation efficiency, particularly for high-mass planets. This further reinforces the idea that the inner galaxy is a hotbed of planet formation.
So it all ties together beautifully. The study essentially unveils a compelling narrative of the Milky Way's evolving capacity for planet formation. Could you summarize this grand evolutionary story for us?
Certainly. Picture the early Milky Way billions of years ago. It was a less enriched environment with lower metallicity, making planet formation less common, especially for large planets. As the galaxy aged, stars lived and died, enriching the interstellar medium with heavy elements. This gradual enrichment led to an increase in planet formation efficiency, allowing planets to emerge further from the galactic center as time went on.
So it's like the Milky Way has become more fertile for planets over time, with the seeds of planet formation spreading throughout the galaxy.
Exactly. The study's findings paint a dynamic picture of a galaxy in constant flux, its changing chemical landscape directly influencing the prevalence and diversity of planets within it.
Before we delve further into the paper's findings, I'd like to pose a question to our listeners. What stands out to you so far? What sparks your curiosity about this intricate connection between a star's galactic history and its potential to harbor planets?
Yeah, it truly is remarkable how a star's chemical composition, age, and birthplace within the galaxy all converge to influence its likelihood of forming planets. The interplay of these factors creates this complex and fascinating picture of planet formation.
Absolutely. The paper doesn't stop there. The researchers, they take their analysis a step further by investigating how these factors impact the formation of specific types of planets, namely high-mass planets like gas giants and low-mass planets like our own Earth.
Right. Yeah, they delved into the formation efficiency of these planet types across varying, metallicities, ages, and galactic birth radii. And by examining these trends in detail, we gain a more nuanced understanding of the diverse pathways that lead to planet formation.
So let's start with high-mass planets. What patterns emerged when they looked specifically at those gas giants?
So the study found that the formation efficiency of high-mass planets is particularly sensitive to both metallicity and galactic birth radius. As metallicity increases, the efficiency of forming these massive planets rises dramatically, almost as if there's a critical threshold of heavy elements required for their formation.
So it's not just about having more building blocks, it's about having enough to cross a certain threshold that allows these gas giants to emerge.
Precisely, it seems that a substantial amount of heavy elements is necessary to trigger the processes that lead to the formation of these massive planets. Additionally, the study found that the closer a star is born to the galactic center, the more likely it is to form a high-mass planet,
It's like the inner galaxy, with its dense environment and abundant heavy elements, acts as a giant planet factory, churning out gas giants with greater efficiency than the outer regions.
Yeah, a very vivid analogy. And it underscores the importance of considering the galactic context when studying planet formation. It's not enough to look at a star in isolation. We must understand its environment and history to fully grasp its planetary potential.
Now, what about low-mass planets? Did they find similar trends in their formation efficiency?
Interestingly, the formation efficiency of low-mass planets exhibited a less dramatic dependence on these factors. While a positive correlation with metallicity was still observed, it wasn't as pronounced as for high-mass planets. The influence of galactic birth radius was also less significant.
So low-mass planets appear to be more resilient, capable of forming in a broader range of galactic environments.
That's one possible interpretation. It could be that the processes leading to the formation of low-mass planets are less reliant on the abundance of heavy elements or the specific conditions found closer to the galactic center. However, more research is needed to unravel the intricate mechanisms governing their formation.
Now let's revisit the concept of galactic chemical evolution. You mentioned earlier how the Milky Way has gradually enriched itself with heavier elements over time. How does this study contribute to our understanding of this grand evolutionary process?
Well, this study provides compelling observational evidence for the Milky Way's evolving capacity for planet formation. In the early galaxy, with its lower metallicity, planet formation, particularly for gas giants, was likely restricted to the inner regions where heavier elements were more concentrated. As the galaxy matured and stars churned out heavier elements through supernovae, the interstellar medium became progressively enriched, expanding the regions where planets could form.
So it's not just about the raw amount of heavy elements, but also their distribution throughout the galaxy. As the Milky Way evolved, the seeds of planet formation were sown further and further from the galactic center.
Exactly. This study elegantly demonstrates the dynamic interplay between galactic evolution and planet formation. The Milky Way's changing chemical landscape over billions of years has directly shaped the diversity and distribution of planets within it.
That brings us to a fascinating question. Where does our own solar system fit into this picture? Our sun resides in a relatively quiet region of the Milky Way, far from the bustling galactic center. Does this study provide any insights into the formation of our own planetary system?
It certainly raises some intriguing questions. Considering the trends observed in the study, our sun's location and age might suggest a lower probability of forming gas giants like Jupiter and Saturn. Yet these massive planets are an integral part of our solar system.
So how do we reconcile their existence with the findings of this study? Could there be other factors at play that contributed to their formation?
It's possible that the formation of our solar system involves some unique circumstances or events that deviated from the general trends observed in the study. Perhaps our sun migrated from a different location in the galaxy, or perhaps a nearby supernova seeded our early solar system with an extra dose of heavy elements, providing the necessary ingredients to form our gas giants.
That's fascinating. It reminds us that while this study offers valuable insights into the broader patterns of planet formation, each planetary system, including our own, likely has its own unique story shaped by a complex interplay of factors.
Indeed, unveiling these individual narratives and understanding the unique circumstances that led to the formation of different planetary systems is a vital and ongoing area of research in astronomy.
In the final section of the paper, the researchers address the limitations of their study and highlight avenues for future research. What are some of the key takeaways they emphasize?
One of the primary limitations they acknowledge is the inherent bias in the sample of exoplanets we've discovered so far. Current detection methods are more sensitive to certain types of planets, particularly those that are large and orbit close to their stars. This means our current understanding of planet formation is likely incomplete, shaped by the limitations of our technology.
So there could be a whole hidden population of planets out there, perhaps even more diverse and intriguing than those we've already detected.
Absolutely. As our detection methods improve and we expand our observational capabilities, our understanding of planet formation will undoubtedly evolve. The authors stress the need for future studies with larger and more diverse samples of exoplanets, particularly those that can detect low-mass planets and planets in wider orbits.
This leads to a crucial question for our listeners. Why should we care about the galactic context of planet formation? What are the broader implications of this research?
Well, understanding how planet formation is influenced by the galaxy provides valuable insights into the prevalence and diversity of planets in the universe. It helps us refine our models of planet formation and guides our search for potentially habitable worlds.
So it's not just about finding planets, it's about understanding where they form, how they form, and what that tells us about the possibilities for life beyond Earth. It broadens our perspective and deepens our appreciation for the intricate interplay of cosmic processes that have shaped our universe and our place within it.
I completely agree. This research reminds us that we are not isolated islands in the vastness of space, but rather products of a dynamic and evolving galaxy. Our very existence is intertwined with the grand narrative of the Milky Way and its ongoing evolution.
And on that profound note, let's pause for a moment and allow our listeners to reflect on the incredible journey we've taken to the cosmos. When we return, we'll explore some of the broader implications of this research and discuss what the future holds for our understanding of exoplanet formation. Welcome back to the Deep Dive. We've been exploring the fascinating connection between a star's galactic history and its potential for hosting planets. And we've discussed the influence of metallicity age and galactic birth radius on planet formation efficiency. But now let's zoom out a little bit and consider the broader implications of this research.
Yeah, this study not only, deepens our understanding of planet formation, but it also provides these valuable insights for the search for life beyond Earth. If the building blocks of planets and therefore life as we know it are more concentrated in certain regions of the galaxy, well, then those regions become prime targets for our search efforts.
Yeah, it's almost like this study provides us with this cosmic treasure map, highlighting the areas where planets and potentially life are more likely to exist.
That's a great analogy. By understanding the galactic factors that favor planet formation, we can really refine our search strategies and increase our odds of finding those elusive planets that might harbor life.
Right, and the implications go beyond simply finding life, though, too.
Yeah.
This research also kind of hints at the incredible diversity of planets that might exist throughout the Milky Way. If planet formation is shaped by, galactic location and time, we should anticipate a vast array of planetary systems. So like anything we've observed in our own solar system.
Absolutely. Imagine planets orbiting stars much older and more metal-poor than our sun, or planets forming in the intensely dynamic environment of the galactic center. These extreme conditions could give rise to planets with compositions, atmospheres, and evolutionary histories, vastly different from anything we've encountered so far.
Yeah, it challenges our preconceived notions of what a planet can be and opens up this universe of possibilities. We might find planets with multiple suns, planets with rings dwarfing Saturn, or planets composed of materials we haven't even imagined.
Precisely, this study underscores the vastness and diversity of the cosmos. And it pushes us to kind of expand our definition of planet and encourages us to embrace the possibility of worlds that defy our current understanding.
This research also highlights a fundamental concept, I think, too, the interconnectedness of everything in the universe. From the smallest particles to the largest galaxies, events are constantly shaping and influencing each other, weaving this complex and beautiful tapestry of cosmic evolution.
Yeah, I couldn't agree more. This study is a beautiful illustration of how these seemingly disparate processes like stellar evolution, galactic dynamics, and planet formation are all intricately linked. And understanding these connections is crucial to unraveling the grand narrative of the cosmos and our place within it.
Now, as we conclude this deep dive, I want to leave our listeners with a final thought-provoking question to ponder. We've been focusing on our own galaxy, the Milky Way, but we know that our galaxy is just one of billions, perhaps trillions of galaxies in the observable universe. So if our galaxy's history and structure influence planet formation, what does that mean for the potential for planets and perhaps life in other galaxies?
That's a profound question, and one that lies at the forefront of astronomical research. If the principles outlined in this study hold true across the universe, well then, the potential for planets, and by extension life, is staggering. Imagine the diversity of planets that might exist in galaxies of different ages, sizes, and compositions.
It suggests that our current understanding of planets, and indeed the universe itself, is merely scratching the surface. There are countless worlds waiting to be discovered, each with its own unique story to tell, each a testament to the boundless creativity of the cosmos.
The universe is a vast and mysterious place, full of wonders that we are only beginning to comprehend. As we continue to explore, we must remain open to the unexpected, to the possibility of worlds that challenge our assumptions and expand our understanding of what's possible.
Thank you for joining us on this deep dive into the captivating world of exoplanet formation. We hope you've gained a deeper appreciation for the intricate dance of cosmic forces that have shaped our galaxy and its planetary inhabitants. Until next time, keep exploring, keep asking questions, and keep looking up at the stars with a sense of wonder and curiosity.